Welcome, welcome, welcome. In this video, we're going to discuss private and public keys. Now, we've already discussed in a previous video an example of a key cipher where we had the key phrase. That was an example of a piece of information that we needed to help us do the encoding, decoding. That's what we mean when we say a key. It's just like in real life when you have a key and you're sticking it into a lock. That's what helps you do the unlocking process. Well, for cryptography, the key here is extra information that we need to do the encoding or decoding. So sometimes this key or this information is called a stream. What it does is combines the plain text, so it's some way of dealing with the plain text with this key or key stream to get the ciphertext. So in this key cipher or stream cipher, the plain text digits are encrypted one at a time. So you take a plain text digit and you encrypt it one at a time. So possibly one of the very first private keys that was used is the auto key cipher from 1585. So what you do with this cipher is you start by picking a seed. So a seed is a single letter. For our course, we're going to use English, so a single letter in the English language. So given a bunch of plain text, what we do with that plain text is get a key stream in the following way. So the very first thing in our key is the seed itself. And then the next key is the very first plain text digit or letter. And so on and so on and so on, until we get to the last thing in the key would be the second last thing in the plain text. So we just keep generating the key with the plain text itself, except it's shifted over one because the very first thing in the key is the seed. So then our encoding and decoding functions are as follows. We just take our mods 26 congruence and we either add the key for the encoding or subtract away the key for the decoding. Now, this isn't a particularly secure cipher for modern use because the kibitzer can simply attack every possible seed that could be out there and then crack the code. But if you'd never heard of the auto key cipher, I suppose that it does provide some sense of security. So let's do some examples. Let's play the role of the sender and receiver using the auto key cipher. So our first word is media. Let's write down the 12. So what we want to do with the 12 is add on the seed, which is 3. So if we add those two together, we get 15. That would be the first item in our ciphertext. So now we'll deal with the 4. And in order to deal with the 4, we need to drag the 12 over because the first thing in the plain text becomes the second thing in our key. So we add those together and we get 16. And we'll continue writing down our word media, so 3, 8, and 0. And we'll continue dragging the previous thing in the plain text to the next thing in the key. So we would get 4, and underneath the 8 we get a 3, and underneath the 0 we get an 8. And our job is to add all of these together. So we'd get 7, 11, and 8. So our letters in our ciphertext would turn into a P, and a Q, and an H, and an M, and an I. So that's the ciphertext that we would send away to our receiver. So now we'll play the role of the receiver. If we received some ciphertext that's sitting right here, what do we do with that to do the decoding? So let's write all those numbers down on our page. And this time we're using a seed, the letter B, so that corresponds to 1. And let's remember we're doing the decoding this time, so we subtract the key. So first we would get 5. And then once we have the 5, that's the first thing in the plain text. And remember, that's what produces the next thing in the key. So we would drag the 5 and subtract and get 0. So then we drag the 0, and we would subtract and get 12. We would drag the 12, and then we would subtract and get minus 12, or we could write 14. So then drag the 14 to get the next thing in the key, and we would subtract 14 to get minus 6, or 20, and then one more time. So drag the 20 over, and we would go ahead and subtract our 20 and get minus 8, or 18. So this should spell something. We should get some kind of word out of this. So if we convert to letters, we have an F, we have an A for 0. For the 12, we have M, O, a U, and an S. So we get the word famous. So that is a summary of the auto key cipher. Let's move on to our next type of cipher. So next, we're going to discuss the Vernam cipher. So the Vernam cipher, what we do is we convert every letter to its binary equivalent that has 5 digits. Notice all of them have 5 digits, even the A. Like you could write A as 0 and just have 1 0, but you need 5 digits for the Z, so there's a consistency of every one of them having 5 digits. Okay, so again, you pick a key stream and you use that key stream to add or subtract to find your encoding and decoding functions. Now, this is done in mod 2. So we just have zeros and ones because it's going to be done in binary. So that makes adding and subtracting the same because we're working in mod 2. So really you can view the encoding function and the decoding function as the same. Now what you have to do to successfully set up the Vernam cipher is to secretly pick a key. And this key is just a bunch of ones and zeros. So all you're doing is taking a bunch of ones and zeros and adding it on to your plain text, and that creates a random bunch of ones and zeros. And as long as the decoder has that key, they can successfully do the decoding. So one of the problems that's occurred when historians have tried to figure out during the years of World War I and World War II, people were using the Vernam cipher to send very secure and secret messages. Sometimes they would say, pick this novel and flip to page 67 and go to line 12, and then all of the letters there will somehow create our key, something along those lines. And there's many ciphertexts that are out there that mathematicians have never been able to crack because we simply don't know what the key stream is. And without the key stream, all you can do as the kibitzer is just randomly guess at all of the possible words of whatever length you have. So the kibitzer can't really do anything, just guess based upon the length of the ciphertext to try to figure out what the plain text is. So this makes the Vernam cipher completely secure if it's set up correctly. So you might say, well, if this one is completely secure, why don't we ever really look at any other ciphers? Why doesn't the battle kind of end in 1917 and we forget cryptography from there on? Because there are further advancements that are coming later along in our timeline. And the answer to that question is, well, this just isn't very practical. Imagine trying to send someone a message and you have to somehow secretly and securely produce another message of the same length, of random ones and zeros. It just doesn't have to be a message, but just a key that's of the same length as your plain text, and you have to get that to both the sender and receiver team. So not only is it sort of not very efficient, where you have to kind of duplicate the amount of information you have to send, you also have to transmit that key somehow effectively. Now, if you can do that and you want something completely secure, well, then the Vernam cipher is the choice for you. But it's not so practical. Now, the previous cipher that we looked at, the AutoKey cipher, was pretty darn practical. You just had to get one seed, and once you got the seed, then you can go ahead and generate the key from there. But the AutoKey cipher is not so secure. So we're going to look at something that is a nice balance between the Vernam cipher and the AutoKey cipher called the RSA cryptosystem. But first, we will discuss a couple examples of dealing with the Vernam cipher. So, how could we encode the word rich and decode the word below? So what you do is you take each digit in this list, working column by column, and you add in mod 2. So 2 ones will make a 0. 2 ones make a 0, and a 1 plus a 0 makes a 1. So if the digits are different, you get a 1. If the digits are the same, you get a 0. So on and so on and so on. 0 and a 1 and a 1 and a 0, 1, 0, 1, 0, 1. And notice there's no carrying. It's not like usual addition where you add 1 plus 1 and you get 2 and you'd carry to the next column. That's not done here. Each column is done individually. Each piece in our ciphertext / plain text is dealt individually together with the key. So we would go ahead and say, here's our list of ones and zeros. That's what we want to send away, and the receiver would have to deal with that, and hopefully would have the key stream to do the decoding and get the word rich back. So below, now we'll play the role of the decoder, of the receiver, and really this encoding and decoding process is exactly the same. You just go through each of the columns and you add up the digits in mod 2. So we've got a 1, a 1, a 0, a 0, a 0, and 1 and 1 make 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0. So if we want to deal with what word this might be, we'd have to convert back to decimal. So a 1 and a 1 makes 3. 2 plus 1 is 3. And that 1 is in the position of 2 to the power 2, so that's 4. And there's nothing in that third letter, and the fourth letter is a 3 again. So we would get D, E, A, D. So our plain text is dead. All right, let's move along to the next cipher, the RSA cryptosystem. So this was published first in 1977, and it is still used in modern cryptography. So the very first thing that you do is you pick 2 prime numbers, and you take those 2 prime numbers and you multiply them together. Now this whole cryptosystem relies on a very important property. If you have the number m and it's made of 2 prime numbers that have been multiplied together, and let's say P and Q are properly chosen and they're quite big numbers, quite big prime numbers, it's very hard to just know M and try to figure out the P and the Q. It might seem like a simple equation right in front of us, but when these numbers P and Q are large prime numbers, it's very difficult to find the P and the Q from just the M. That's really where the whole security behind this system lies. If anyone was able to figure out a convenient way of solving this problem that always worked, that could take the M and figure out the P and figure out the Q that produced that M, then really our whole system would shut down in terms of security online. If you've done online banking, or if you've done online shopping or logged in to something securely, you're using the RSA cryptosystem in some sense, and it's relying on this problem. So if this problem was solved, all of a sudden all this security that we feel like we have would just fall by the wayside. So there's going to be two important numbers going forward, the m value, which we've talked about, and the n value. So the n is found by multiplying the two primes together minus 1. The n is going to be an important mod for picking the powers below, and the m will be the mod that we use for the encoding and decoding. So in the next 2 points, we're going to think about picking an encoding power and a decoding power. So what we have to do is think mod n for these two things, and below we'll think about mod m. So mod n, we need to pick an encoding power e from 0 and then 1 less than the number n. So this e value, it has to have an inverse in mod n. And that inverse gives us the decoding power. And of course, the inverse e times d should be 1 in mod n. So once you have that encoding and decoding power picked, then that forms your encoding and decoding functions. So the encoding function is simply raised to the power e, and the decoding function is simply raised to the power d. But let's remember that those congruences are done in mod m. And m is p times q, the two prime numbers multiplied together. And the same with the decoding function. So e and d, in summary, are chosen to be values in mod n, and the encoding and decoding is done in mod m. So as a quick summary of what we've talked about previously, the encoding function is usually something that we keep secret. We don't want people to find out about the encoding function. Don't tell anyone this encoding, decoding business is secret. Well, that's kind of the opposite in the RSA cryptosystem. It's what we call a public key cryptosystem. In the previous examples that we looked at, in the Vernam cipher and the AutoKey cipher, we didn't want people to know the seed. We didn't want people to know what that key ended up being in the Vernam cipher. But that's very different from the RSA cryptosystem. In the RSA cryptosystem, we say, hey, here's my encoding function. We put that information out there. It's public. It's like your name. Anyone want to call you up, just call me by my name. Here it is. I'm out there. I'm exposed. So you might say, well, how does this public key cryptosystem actually provide security if the encoding function is out there for everyone to see? Well, the idea is that even though the encoding function is out there, only you know how it was built with these prime numbers and can do the decoding when things are sent to you. So this idea makes the RSA cryptosystem extremely secure. As long as we correctly choose the P and the Q, they do have to be large enough and carefully chosen. You don't want like twin primes, for example. You don't want these P and Qs to be chosen very close together to each other. But in general, you pick two random big prime numbers, and most of the time you're going to have a very secure public key cryptosystem set up. So, and if you do that, it's really next to impossible for the kibitzer to find out the decoding function from the encoding function, like we were talking about before. And there's many computers that are kind of working away at these problems as we speak to try to crack the code and figure out how to factor a P and a Q that are out there and we don't necessarily know what they are. So let's look at an example. Let's take the characters from our course. We've got Dr. Echo, Professor Scarlett, and Evangeline, and they've set up the following RSA cryptosystem. So over here on the right-hand side, we have public information. So this information is what everyone gets to see, the whole world gets to see these encoding functions. And the idea is that there's some private hidden information on the left-hand side that only Evangeline knows. Now, I've picked small numbers here so that we can just kind of see what's going on. In reality, you'd never pick 21. That's way too small. But we can see that, okay, the secret numbers are 3 and 7 that build you 21. or 3 and 13 to build you 39. And really the only way that you know like 21 factors into 3 and 7, you probably just know that by dealing with these numbers throughout your whole life, some kind of recognition by memory. But there's no sort of formal system for taking the 21 and producing the 3 and the 7. And that's the whole idea here. Now, we can see once we get to 5,353, maybe it's already a little bit more difficult to verify that, oh, these are the two prime numbers that build that number. So as a very first question to start us off, let's try to think about why Dr. Echo can't use the encoding power of 5. So Evangeline and Professor Scarlett used 5. Dr. Echo cannot use 5. So try to explain why. Pause the video now and see if you can figure it out. I'll give you the answer in just a moment. Okay, so let's remember from above, when we're thinking about picking our encoding power, the important mod to think about is the mod n, the n value. So for n, it's p minus 1 multiplied by q minus 1. So for the case of Dr. Echo, that would be 53 minus 1 for 52, multiplied by 101 minus 1, so 100. So Dr. Echo's n value would be 5,200. Now let's remember from above, if we just scroll back up there, when we're picking our encoding and decoding powers, we do need to make sure that we pick E so it has an inverse. Our encoding power has to have an inverse, and the same with the decoding power, it has to have an inverse as well. So looking below, the question asked, why can't we pick 5? Well, 5 and 5,200 are not relatively prime, and that's the problem. So since it's not relatively prime, with 5,200, 5 also does not have an inverse in mod 5,200, so we can't use that as our encoding power. Okay, so now that we've reminded ourselves of how to properly pick the encoding function, let's do some encoding / decoding on the next page. So let's say Dr. Echo wants to send Evangeline a secret message. Evangeline is often getting herself into trouble, getting kidnapped like earlier on in the course. So Dr. Echo says to Evangeline, run, but doesn't want to have that word exposed, doesn't want the criminals to be informed that Dr. Echo is onto them, so is wanting to encode this message. So let's see if we can go ahead and do that. So what we'd want to do is write down our encoding function here. So encode R and encode U, and we'll encode N. And we're sending it to Evangeline. So let's remember, for Evangeline, what we're going to do is use mod 21. So all these congruences that we just wrote down here, let's remember that all of those congruences are done in mod 21. So that's where we're writing mod 21 at the bottom of our problem here. And to send things to Evangeline, her encoding power was 5. So we would take R, which is 17, and raise it to the power 5. And U, which is 20, raise that to the power 5. And for N, that's 13, we'd raise that to the power 5. So let's practice our modular arithmetic. I want you to try to reduce these down to their corresponding remainders in mod 21, and then we'll give the answer in just a few moments. Okay, so I don't have a calculator in front of me, and I don't know what 17 to the power 5 is off the top of my head. So I'm going to try to reduce this in a little bit more of a convenient way. I'm going to write 17 as minus 4, and there's 5 of them. So I'm going to square minus 4, and then square it again. So that's 4 of them. and then there's an extra one left over, so there's another minus 4. So that's 5 minus 4s multiplied together. So minus 4 times minus 4 is 16. So we have 16 squared multiplied by minus 4. Now 16 in mod 21 is the same as minus 5. So we get minus 5 squared. And minus 5 is the same as 25. So 25 multiplied by minus 4. And 25 is the same as 4 in mod 21. So finally we get minus 4 times minus 5 for minus 16, or 5. So we get 5 as a result for R. Now for U, we have 20 to the power 5, so that's the same as minus 1 to the power 5. So it's very convenient for us to just calculate out that that's minus 1, and this does return us right back to 20 where we started. And for 13, how about we do something similar to what we did for 17 above. 13 is the same as minus 8, so we'll square that and then square it again for 4 of them, and then we'll have to multiply that by 13. So minus 8 squared gives us 64. So 64 squared times 13. Now 64 is kind of convenient in mod 21 because 64 is 1 more than 63, which is a multiple of 21. So that changes into 1 squared multiplied by 13. So we return right back to where we started at 13. So we end up getting in our ciphertext 5, 20, and 13. So that converts to F and U and N. So Dr. Echo was maybe extra clever here. The ciphertext itself looks like a word and is hidden on another layer, is just saying to Evangeline to have some fun. But if she's going to use her encoding and decoding system that's been set up, she'll get the real message behind the scenes. So now that we've played the role of the sender, send away the word fun, let's try to switch over to playing the role of the receiver. So if Evangeline is going to receive this message of fun, how is she going to deal with it to get it back to the plain text that it's supposed to be? So Evangeline's private decoding function, what is that? Well, let's just scan back. Let's remember our table from above. Here's our table. Evangeline has that encoding function and has picked these prime numbers, but has not yet, written down over here and privately what the decoding function is. Everything is set up correctly. We just need to think about what is Evangeline's decoding function. So let's go back. For Evangeline, we need to first think about what is Evangeline's n value. Remember, the n value is the one that we use to set up the encoding and decoding functions. So Evangeline's n value is p minus 1, q minus 1, so 6 times 2 for 12. So Evangeline's encoding value for her encoding function is 5. So the question is, what is the corresponding decoding number? So what we need to do is invert E. We need to find the inverse of E in mod n, which is 12. So what we can do is write 1 down on our page and say, okay, how can I factor 1? So let's add 12, and we get 13. Okay, that didn't help very much. 13 is a prime number, but we can go right ahead and add 12 again, and we get 25. Well, this will work. 25 is 5 times 5, so 5 times 5 gives us 1 in mod 12. Let's make sure that we write mod 12 at the end of this line of congruences, because the encoding from above was done in mod 21, and we're kind of switching back and forth from mod 21 and mod 12. So the D value is also 5. So that means that our corresponding decoding function is d of x congruent to x to the power of 5 as well. And let's remember that's done in mod 21, right? That's done in mod m. So reminding ourselves that mod n here is 12 and mod m is 21. So now that Evangeline has this nice decoding function set up, she can go ahead and use it to do the decoding and decode the word fun. So that's what we're going to do below. So we want to decode f, and we want to decode u, and we want to decode n. So we'll just set this up. So f is 5, so we'd raise 5 to the power 5, and u is 20, so we'd raise 20 to the power 5, and n is 13. We'd raise 13 to the power of 5. And let's remember all of this work is done in mod 21. So again, I'm going to get you to go ahead and practice your modular arithmetic. Give this a try, pause the video now, and see if you can get the answer. I'll give it to you in just a few moments. Okay, so again, I don't have a calculator in front of me. I'm just going to deal with 5 to the power 5 the best I can using my head. So 5 times 5 is 25. So we have 25 squared, and then an extra multiplying by 5 is in order. So 25 in mod 21 does go ahead and reduce to 4 for us. So 4 squared times 5. And 4 is 16, so 16 times 5. And 16 is the same as minus 5. So we have minus 5 times 5. And then we get minus 25. And then adding 21 a couple of times will give us 17. So we did get the word, or the letter of the first word that we're looking for as 17, which is R. Now 20 to the power 5, we've actually already done that work above. From the work above, we know that that just returns us to 20. And 13 to the power 5, same thing there. There was no change. We got 13 as well. So if we put this all together, we do get the word that we're looking for. Evangeline is going to run from any danger that might be approaching. So each of the lectures that we've looked at on cryptography have had a bit of a theme. And the first theme that we looked at was quotes, and then we had a bit of a pizza lunchtime theme. With this lecture, the theme is a little bit harder to notice. So I'm going to zoom out for us now and take a look at these words that are here. So I was thinking that if one of my future students or current students was ever able to solve this problem of being able to factor a number that was built of two large prime numbers, there would be some words or messages that I would like to have that student know. So the first thing, if you were able to solve that problem, the media would be very interested in you. And you would probably become famous very quickly. And with all that said, you would very likely become rich, but unfortunately, that also might make you become dead. You should definitely run. Thanks so much for listening, and we'll see you on the next one.